Good morning, everyone. My name is Aleksandra Cebrat from SuSoS AG in Switzerland. We are one of the partners of the AAA Code project, and today with my talk on the water-based adhesion promoters for multi-material interfaces, I would like to shortly introduce to you our company and how we contribute to AAA project, but also to give you some general information on what we bring to the various fields as a company. To give you some small details, SuSoS started its work in 2004 in Zurich, so we are now more than 20 years on the market, dealing with analytic and polymer coating services. We observe the needs and tune our products to various customers from really different fields. We work mostly with monolayers, so the scale of nanometers, under controlled laboratory conditions, so clean rooms, and ensure the maximum quality of our coatings and polymers. We work close with all our partners and clients to design or study and if need scale up production, so we always make sure that we understand what clients do and we tune our products to their needs. And thanks to use of automated robots we have in our laboratory, we can scale up processes and save time when we require it or when the production is extremely large. Of course, we are always open to audits to check what we do. During the long time of gaining experience, we understood that surface matters, and it matters a lot. It matters on the microscopic and nanoscopic scale, and to influence the various functions at the surface, different coatings are used. What happens at the surface? Well, reactions occur at the surface, not in the bulk. The surface area, roughness, and chemical composition determine how reactive a material is. Moreover, the surface controls how a material interacts with its environment. For example, we have hydrophobic and hydrophilic surfaces affecting wetting. We have friction, adhesion, and wear in mechanical systems. It influences biological effects like cell adhesion, protein binding, and biocompatibility. And when materials are very small, and we talk here about nanometer scale, nanoparticles, surface to volume ratio becomes huge. So surface properties dominate behavior almost completely. Due to all that, we know that surfaces are tough, as there are many materials and properties that can be achieved. And even atomic size contamination can play a huge role. And to achieve all that we need, we know that we first need to understand how things work to aim for the solution. Of course, coating itself and synthesis of the polymers is one challenge, but the other one is the control and assessment of the surface and of the coating itself. And here at SuSoS we have various possibilities to assess those two parameters. We have the X-ray photoelectron spectroscopy and time-of-flight secondary ion mass spectroscopy to check the surface chemical characteristics. We have the variable angle spectroscopy ellipsometry to assess the thickness of the coating. We have particle count, quartz crystal microbalance. We have microtribometry and bioindentation for the physical and tribological properties of the materials, as well as dynamic contact angle for checking the hydrophilicity and hydrophobicity of the surfaces, and the various microscopes and profilometers. As you can see, the possibilities and the issues are limitless. And SuSoS engages in many fields where surface is of huge importance. Ultra-stable biosensors, high-accuracy diagnostics, organ-on-chip systems, medical devices where low frictions is of big importance, as well as no foulingness, and bonding, for example, in microfluidics, or, as we will talk later, in the AAA project, where we want to ensure the stability and the robustness of the main coating, which is a nanocellulose, to various surfaces that can be found in the bus. So why do we even need adhesion promoter? I told you a little bit already what they can do, but I would like to give you here the example from the AAA project. So we in this project would like to deposit the nanocellulose on the bus, and that way have the antimicrobial, antibacterial properties inside the bus, so the public space. And we try spraying CNC, so crystalline nanocellulose, on the plastic foil that we could then, for example, stick to the various places in the bus, and so like a sticker with the antimicrobial coating. However, what we observed after spraying is that if such a coating dries, we observe the peeling of the cellulose from the substrate. There is completely no adhesion. However, if we apply one of the adhesion promoters here at SuSoS and then spray the cellulose on top, we have a very good stable coating. So the foil, the substrate, can be easily creased and manipulate without causing the nanocellulose to unglue from the foil, all thanks to the adhesion promoter. So what is an adhesion promoter? It's a material, in our case a polymer, that is deposited as a monolayer between a substrate and another layer, giving us a different function of the surface. Depending on our need, we can design the polymer, and this polymer will give us different functions. Of course, we already know that there are various substrate and ad layers, so the materials that we want to deposit on the substrates. For example, we want to bind glass with nanocellulose, glass with glass, or steel with nanocellulose. And very often the compatibility and possibility to bond them without functionalization is impossible. In that case, we need to find a bridge, the adhesion promoter, that will on one side anchor the ad layer to the according substrate, and on the other side of the adhesion bridge bind the ad layer, the additional coating that we want to put. And as you can see, depending on the material of the substrate, and also the coating on top, polymer, nanocellulose, etc., we use different groups. So for substrate binding, we have amines, silanes, catechols, thiols, whereas for the top, so the ad layer, polymer or nanocellulose coating, we use various diazerines, bezophenones, and azides. And in our case at SuSoS, we use azide as the bonding group to the ad layers. Here I would like to introduce to you the Akibond technology, water-soluble superglue. The Akibond technology is based on the AsiGrip reactive molecular platform. So the Akibonds carry the AsiGrip SuSoS proprietary azide group. This group is UV and temperature reactive and capable of covalently binding to surrounding CC, CO, CH bonds and similar. And the AsiGrip itself, the AsiGrip group, it cross-links to form robust monolayers, 2.5D monolayers, if used on the plane surface, and can act as the adhesion promoter in presence of the other polymers, as well as a cross-linker to form gels of tunable thicknesses or stiffness. And depending on the needs of our clients, we can use it as the bioadhesive, the non-fouling coating, for cross-linking, for bonding, reacting with the click chemistry, and many other possible applications that our clients have. So how do we apply Akibond coating? So we prepare first the surface. We can use plasma here, plasma treatment, UV, corona, wet processing to get rid of the contamination on the surface. Then we deposit the Acibond from water or alcohol solution if it's needed by various techniques, be it dipping, painting, rolling, spraying, as we do with in the AAA project, printing, jetting, etc. So we deposit the monolayer of the Acibond that way. Then we can functionalize by depositing any other polymer from any solvent, be it inorganic or organic solvent. And we post-process it by curing, as I said, with UV, or as it is for the first class of Acibond polymers, using temperature. This temperature is above 90 degrees Celsius. And such a sample can also be sterilized if needed. So how does the acid grip work with the azide group? So we have the azide that need an activation energy, which is UV light or heat. The temperature depends on the class of the acid grip group. And we form the nitrines. Then form the covalent bond between the N from the azide group and the CC, CH, etc. of the neighboring polymer, that is the add layer, and that way we immobilize the material on the surface. Interestingly, this is a non-specific nitrine insertion to different polymers, so we can bound our adhesion promoter to various polymers without the synthesis of complex adhesion promoters. Here, the short example of how we can use the Acibond with the acid grip group for bonding of two different substrates. It's a polymeric substrate, so COP and COC foils. What we do is we take the foils, we apply the Acibond primer to the substrate materials, then we press both materials together and irradiate it with the UV. And as you can see, upon the heat, upon the UV illumination and upon the pressing of the press, the two materials can bond together. And as you can see here, there is a cohesive failure, so the material rips due to the strength of the bond between the two foils. So there is not a failure in the adhesion layer, but in the material that is far less strong than the glue in between. But what can we do if we use the polymers with a low glass transition temperature, like COC, PMMA, PET, etc., that have the transition temperature at around 100 degrees Celsius, which is the temperature below the activation temperature of the azide group on the acid grip proprietary SuSoS proprietary group. In that case, we designed and synthesized a low temperature, so below 90 degrees or around 90 degrees, activated azide containing adhesion promoter. It's the Acibond second class of Acibonds. So now we solve the problem of the usage of the plastic with the low glass transition temperature. But what if we cannot use plasma, so the surface pretreatment? For example, we want to coat the bus as we want to do it in the AAA. So we have no equipment, the surface is too big, maybe we cannot put our sample into plasma due to possible contamination of the plasma. Well, for that, we established a protocol for the non-plasma treated surfaces, and we used the hydrophobic interaction to assemble the Acibond on surface, and upon UV or temperature curing, the polymer forms a covalent bond with the substrate. So how do we apply this new class of Acibonds? Well, we can use various polymers, various plastics, PMMA, PP, PET, etc., hydrophobized surface, or glass. So no plasma here. Of course, it will also work with the plasma if we want to, but here the main goal is to use no plasma. We can here use the same dip and rinse, or for the spontaneous assembly from water, we can use spraying, we can use painting as it was before. We cure at low temperature from 70 degrees onward, so we can avoid the glass transition temperature of plastics, or we can also here use the UV light if it's a preferable method. The same polymer can be used here as a cross-linker, same also from water application, and the add layer, so for example the nanocellulose can be deposited from both organic and inorganic solvents, so water, toluene, ethanol, etc., etc. And here I would like to show the example of how we could increase the robustness of the nanocellulose coating for the 888 project. So we have a plastic slide, a plastic surface, and we try to deposit on top the CNF, so the fiber nanocellulose. And as you can see, if we don't use anything, just the substrate with the nanocellulose, we have the scratch force of approximately 3 Newton, which is very low. If we now use an adhesion promoter, in this case we use the plasma protocol with the acid grip polymer with the acid grip group as an adhesion promoter and also as the cross-linker, so mixed with the nanocellulose, we achieve far better scratch resistance. However, if we try our non-plasma protocol, which would be far more suitable to be used in the baths, and we try using the AccuBond with the low temperature activation acid grip group with the CNF mixed with the cross-link with the polymer that has the acid group inside, we can already go to the approximately 7 Newton upon the UV curing, which is increasingly better than the previous case. If we use both for cross-linker and for adhesion promoter the AccuBond with the acid grip low temperature activation group, upon UV curing or temperature curing, we achieve 9 to 10 Newtons, which is very good for our, it's a very robust coating and can be easily used as a coating in the bath. So the non-plasma protocol and the new class of adhesion promoter and cross-linker AccuBond with the low temperature activation works very well. So with all that, I hope that I proved to you that thin film coatings, monolayer coatings, can be easily applied to the surface to functionalize it. And in general, they can give us multiple functions, bond multimaterial layers, provide long-term hydrophilization, change the contact angle, reduce the non-specific response, no foulingness, increase the mechanical stability as we had it for the AAA project, and many others depending on what is needed. And with that, I would like to finish my presentation. In case of any additional questions, do not hesitate to contact Samuele Tossati or me if you want to know more. Thank you very much.